Welcome to the deep dive. Today we're diving into a really quite fun area of number theory. Happy numbers.
It sounds cheerful, doesn't it?
It does. So what's the basic idea here?
Well, a happy number is essentially a positive integer, where if you repeatedly sum the squares of its digits.
Okay, square the digits, add them up.
Exactly, and you keep doing that with the result. If you eventually land on the number 1, the original number is called happy.
Okay, give me an example, like 13.
13 is perfect, so 1 squared is 1, 3 squared is 9.
Add them, 1 plus 9 is 10.
Right, now repeat. 1 squared is 1, 0 squared is 0.
Add those, 1 plus 0 is 1, we hit 1.
So 13 is happy, yes.
But not all numbers are like that, right? What about, say, 4?
Good counterexample. Let's try 4. 4 squared is 16.
Okay, now 1 squared is 1, 6 squared is 36. No, wait, 36. So 1 plus 36 is 37.
Correct, keep going. 3 squared is 9, 7 squared is 49, 9 plus 49 is 58.
5 squared is 25, 8 squared is 64. 25 plus 64 is 89.
And we keep going. 8 squared plus 9 squared is 64 plus 81. That's 145.
Then 1 squared plus 4 squared plus 5 squared. 1 plus 16 plus 25 equals 42.
Almost there. 4 squared plus 2 squared is 16 plus 4, which is 20.
And finally, 2 squared plus 0 squared is 4 plus 0, which is 4. We're back where we started.
Exactly. It falls into a cycle. 4, 16, 37, 58, 89, 145, 42, 20, and back to 4. It never reaches 1.
So 4 is unhappy.
Unhappy, or sometimes called sad. Yes. It seems like a simple game, but it actually connects to some deeper mathematical ideas.
Right, you mentioned arithmetic dynamics. It's about how numbers change when you keep applying a rule.
Precisely. We're iterating a function. In this deep dive, we'll explore this not just in our familiar base 10, but other bases too, and even look at happy primes.
Okay, let's get a bit more formal. This rule squaring digits and summing them. How do mathematicians write that down?
We use a function, often denoted f sub p, comma b of n, f sub b sub n.
Whoa, okay, break that down.
Sure.
Yeah.
N is the number we start with.
Yeah.
B is the number base, like base 10 or base 6. And p is the power we raise the digits to. For happy numbers, we're squaring, so p is 2.
So for our standard happy numbers, it's f sub 2010 sub.
Exactly. F sub 2, comma 10 of n. And we say n is b happy if applying this function repeatedly. Maybe j times.
Like f sub 2 b sub applied j times.
Yes, sometimes written f sub 2 sub n if that eventually equals 1.
Got it. So our earlier example, 19, 1 squared plus 9 squared is 82. That's f sub 2010 sub 19.
Right, then f sub 2010 sub 82 is 68, f sub 2010 sub 68 is 100, and f sub 2010 sub 100 is 1. So 19 is 10 happy.
Okay, and this works in other bases too. You mentioned base 6.
It does. Let's take a number, say 347 in our usual base 10.
Okay.
In base 6, that number is written as 3035, so 1335 base 6.
Right, because base 6 uses powers of 6. Well, 16 plus 336 plus 36 plus 51, that's 216 plus 108 plus 18 plus 5 plus 347.
Add those up. 1 plus 9 plus 9 plus 25 equals 44. That's in base 10.
Correct. Now, what's 44 in base 6? It's 136, 1 6, and 2 1s. So 112 base 6.
Okay, 112 base 6. Repeat the process. Digits are 1, 1, 2. Square them. 1 squared, 2 squared. That's 1, 1, 4.
Sum is 1 plus 4 equals 6. Base 10 again?
And 6 in base 10 is written as 10 in base 6. 1, 6, and 0 ones.
Ah, okay. Last step.
Digits 1, 0. Square them. 1 squared is 1, 0 squared is 0. Sum is 1.
We reached 1. So 347 in base 10 is 6 happy.
That's right. Or you could say 1335 base 6 is 6 happy. The process is the same.
That's really cool. So are happy numbers, like, common or rare?
Well, in any base greater than 1, there are actually infinitely many happy numbers.
It's infinitely many. How do we know that?
Because 1 itself is always happy, right?
Yeah.
1 squared is 1. And also, any power of the base is happy.
Like 10, 100,000 in base 10.
Exactly. 1 squared plus 0 squared is 1. 1 squared plus 0 squared plus 0 squared is 1. They all go straight to 1.
Oh, and adding zeros doesn't change things, does it? Because 0 squared is 0.
Precisely. If 7 is happy, then 70 is happy, 700 is happy, 7,000 is happy. Because 7 squared plus 0 squared is the same as 7 squared.
Okay, so there are infinitely many. But what about their density? If I just pick a random number in base 10, what are the chances it's happy?
That's a much trickier question, actually. If you look at, say, the first million integers,
Yeah.
the proportion that are happy is around 15%, about 0.15. This is often called the natural density.
So about 1 in 7 numbers.
Roughly, yes. But here's the really surprising part. It's been proven that 10 happy numbers don't have an asymptotic density.
What does that mean exactly? No asymptotic density.
It means that the percentage doesn't settle down to one specific value as you look at larger and larger ranges of numbers. It keeps fluctuating.
Really? It doesn't converge?
No. We know the density is always somewhere between about 0.113 and 0.184, roughly 11% and 19%, but it never picks a single number to approach. It
Yeah,
just keeps wobbling between those bounds.
that is deeply weird. Why would that happen?
It likely has to do with the somewhat irregular way numbers fall into that path towards 1. It's not evenly distributed enough for the density to stabilize. It's one of those areas where simple rules create complex, slightly unpredictable behavior.
Fascinating. Okay, you also mentioned happy bases. What's that?
A happy base is a base b, where every single positive integer is b happy.
Every number eventually goes to 1.
Yes, every number.
Yeah.
It's a very strong condition. And figuring out which bases are happy is actually an unsolved problem in mathematics.
An unsolved problem from this simple idea.
Indeed. What we know is limited. The only integer bases less than 500 million that have been found to be happy are base 2 and base 4.
Just 2. Binary and base 4. Out of 500 million.
As far as we know, yes.
Why base 4, for instance? What makes it special?
In base 4, if you look at the numbers you can get by summing squares of digits, the only number n, where f sub 2004 sub n is the number 1 itself, it's the only positive fixed point.
Yeah.
And crucially, there are no cycles either. In base 4, no matter what number you start with, if you repeatedly apply the sum of squares of digits rule, you are guaranteed to eventually hit 1. There's nowhere else for the process to go long term.
So no unhappy cycles like the one we saw with 4 and base 10.
Correct. Every number is what's called a pre-periodic point for 1. It eventually leads to 1.
That makes sense. So for bases that aren't happy, like base 6 or base 10, the unhappy numbers must end up in cycles.
Yes, exactly. For base 6, it turns out there's only one cycle for unhappy numbers, apart from the fixed point 1.
What is it?
It's a cycle of 8 numbers. If you write them in base 6, they are 5, then 41, then 25, 45, 105, 42, 32, and 21, which then goes back to 5.
An 8-number loop, and every unhappy base 6 number ends up there.
That's right. And just like base 10, in base 6, the only positive number and is equal to the sum of the squares of its own digits, f sub 26 sub n, is 1.
And the base 10 cycle we found starting from 4, what were all the numbers again?
That's also an 8-number cycle. It goes 4 Uri, 16 Uri, 37 Uri, 58, Uri 89, Uri 142, 20, and then back to 4.
And all unhappy numbers in base 10 eventually fall into this specific loop.
Correct. And similar to base 6, the only positive integer n in base 10, such that f sub 2010 sub n, is just 1.
So for any base, it seems a number's fate is sealed. Either it happily finds its way to 1, or it gets trapped wandering forever in an unhappy cycle.
That's a very good summary of this situation, yes.
Okay, let's zoom back into base 10. Any fun facts or patterns about the happy numbers themselves? How many are there up to, say, 1,000?
Up to 1,000, there are exactly 143 happy numbers in base 10.
143, okay. And some examples below 100. We had 1, 7, 10, 13, 19.
Also 23, 28, 31, 32, 44, 49, 68, 70, 79, 82, 86, 91, 94, 97. Quite a few.
Wait, you said 31 and 32? They're consecutive.
They are. That's the first pair of consecutive happy numbers.
Is that rare? Are there others? What about 3 in a row?
The first time you get 3 consecutive happy numbers is much later, 1880, 1881, and 1882.
Wow, okay. Can you get like 4 in a row? Or 10? Is there a limit?
Actually, no limit. It's been proven that sequences of consecutive happy numbers exist for any natural number length. You want million consecutive happy numbers. They exist somewhere out there.
That's incredible. Do we know where they start?
We know the starting number for the first run of length n for small n. For n1, the run starts at 1. For n2, it starts at 31. For n3, it starts at 1880.
Okay.
And here's something really curious. The start of the first run of 6 consecutive happy numbers is the same number as the start of the first run of 7 consecutive happy numbers. A very, very large number. But it's the same starting point for both lengths.
That seems mathematically quirky.
It is rather unexpected, yes.
You mentioned counts earlier. How many are there? Up to 10? 100 and 1,000?
Up to 10, there are 3. 1, 7, 10. Up to 100, there are 20. Up to 1,000, as I said, 143. And it grows from there. By the time you get up to 10 to the power of 20,
Okay, a huge number.
there are over 12 quadrillion 10 happy numbers. So about 12 times 10 to the 15.
Still roughly following that fluctuating density, I suppose.
Presumably, yes.
All right, shifting slightly. What about happy primes? I assume that's just a number that's both happy and prime.
You got it. A b-happy prime has to satisfy both conditions. It reaches 1 using the sum of squares rule in base b, and it's only divisible by 1 in itself.
Does primality interact strangely with happiness?
Well, one interesting thing is that rearranging the digits of a happy prime doesn't guarantee you'll get another prime, even if the rearranged number is still happy.
Ah, right. You mentioned 19 earlier. It's happy and prime.
Yes, 19 is a 10 happy prime. Rearrange the digits to 91.
Still happy because 9 squared plus 1 squared is 81 plus 1, which is 82, and we know that leads to 1.
Exactly. But 91 is not prime. It's 7 times 13.
Good point. Okay. Are there happy primes in all bases?
Well, remember base 2 and base 4 are happy bases.
Where every number is happy, right?
So in base 2 and base 4, all prime numbers are automatically happy primes.
Makes sense. What about base 6?
In base 6, there are 6 happy primes. Examples below, 1296, which is 6 to the power of 4. Numbers like 211 base 6, 121 base 6, 1335 base 6 are all both prime and 6 happy.
And back to base 10. Examples.
Sure. Below 500, we have 7, 13, 19, 23, 31, 79, 97, 103, 109, 167, 193, 239, quite a list. 263, 293, 333, 331, 367, 379, 383, 397, 409, 487.
Plenty of them. Are there like famously large ones?
There are. In 2005, Paul Jobling discovered a palindromic 10 happy prime.
Palindromic. Reads the same forwards
Here.
or backwards.
And it has 150,007 digits.
Wow. How can such a huge number be happy, squaring all those digits?
It has a lot of zeros in it, which helps keep the sum of squares relatively small. And as of 2010, the largest known 10 happy prime was actually Mersenne prime. 2 sub 43,112,609 digits to be precise.
That's staggering. And just briefly, other bases, say base 12.
Base 12 uses digits 0 through 9, then usually X for 10 and E for 11. The first few 12 happy primes are numbers like 1131 base 12, 12333E base 12, and 13011 base 12.
Okay. This has been quite a tour. We even saw a mention of Python code in the outline for checking happiness.
Yes. Computationally, it's fairly straightforward. You basically implement that sum of squares function, f sub 2 pred sub n. Then you just repeatedly apply it to a number.
And you need to check two things.
Right. Does it ever hit 1? If yes, it's happy. But you also need to check if it repeats a number you've already seen in the sequence.
To detect those unhappy cycles, like the 4 minus 16, 4 minus 4 cycle.
Exactly. If you hit a number you've seen before, and it wasn't 1, then you know you're in a loop and the number's unhappy. You usually keep track of the numbers generated in a list or set.
It's interesting how this concept, which feels almost like a recreational math puzzle, has popped up elsewhere. Didn't the outline mention games and TV?
It did. Apparently, the unhappy cycle, starting with 4, appears as part of a puzzle in the Professor Layton video game series.
And Doctor Who.
Yes, in an episode called 42, the solution to a critical problem, essentially a password, was a sequence of happy primes.
That's fantastic. It shows how these neat mathematical ideas can capture the imagination.
Absolutely. They have a certain elegance.
Well, this has been a truly fascinating depth dive. We've gone from the simple definition of happy numbers repeatedly summing squares of digits to seeing this division into happy numbers reaching 1 and unhappy ones caught in cycles.
We touched on different bases, the infinite nature of happy numbers, yet the elusive density.
Right, that non-converging density is still baffling. And the idea of happy bases, with only 2 and 4 confirmed out of so many possibilities, and it being an unsolved problem.
And then combining happiness with primality to get happy primes, including some astronomically large examples.
It really is remarkable how such a, well, seemingly simple starting point can branch out into complex behavior, unsolved questions, and even pop culture references.
It's a testament to the richness hidden within number theory. Even playful definitions can lead to deep mathematical waters.
So for you, the listener, maybe this sparks some curiosity. You could try exploring happiness in base 3 or base 5. See if you can find the unhappy cycle there.
Or investigate those consecutive happy numbers. Or, if you're inclined, perhaps try coding up that is-happy function yourself.
There's always more to explore. Sometimes the most interesting journeys in mathematics start with a single, simple question about numbers. Thank you for joining us on this deep dive.